Hello again. Next, we're going to look at search models. Search models are a whole set of frameworks where we're assuming that there are certain frictions involved so that there may be two parties to a transaction who may find it costly to meet. This is going to mean that in general these models are not going to be efficient. The welfare theorems are not necessarily going to apply. We're going to start by looking at a very simple model of search, a one-sided search model where you just have a worker who is looking for a job and the jobs come out of some distribution. However, in general, we'll like to be able to say where those wages come from, and that will lead later to a two-sided search model that we'll get to if we have time. So let's take a look. To get a handle on how search models work, let's start with a simple one-sided search model in which you have a 0-1 continuum of workers, which basically means there's a population of mass 1 and each worker is infinitesimal. They are small relative to the market. These workers may be either employed or unemployed at any particular date in time. They have utility, instantaneous utility, that is, each period U of C, where CT is consumption as usual. And we're going to say time is discrete for now, as usual. In search models, very often we're going to assume a particular function for this, which is simply linear utility. And the reason is because we're interested in understanding labor market dynamics. We're not interested in understanding the agent's risk behavior. And so we abstract from it by just making utility linear. Of course, if we were interested in understanding how agents deal with labor market risk, then we wouldn't want to do this. We'd want to have some sort of utility function that does have curvature. But since we're not right now, let's forget about it. Agents also discount utility using a discount factor beta. Equivalently, we'll be able to say that they discount the future using some discount rate R, which satisfies this relation. And this formulation is going to be easier and more practical for reasons that we'll look at later. Now, each worker is either employed or unemployed. If unemployed, then C consumption is equal to some benefit B. Now, B could be interpreted as an unemployment payment. B could be interpreted as a home production value. B could be interpreted as a combination of those things plus leisure that the agents enjoy while they're not working. In the one-sided search model, it's not going to matter because the one-sided search model is not general equilibrium. How so? Well, the worker, if they're unemployed, gets a job offer W, where W is the wage that they're going to be paid. And that job offer W is from some distribution F of W. So F is a probability distribution function. If you wish, we could say that it has a cumulative distribution function of F. So far, we've been talking in terms of cumulative distribution functions or measures, whatever you prefer. And we assume that the support of the wage is between 0 and some W upper bar. The job offer pays wage W until it ends, and jobs end with probability lambda, which is exogenous. We can endogenize it if we wish. So what happens in each period? First, workers get W or B, depending on whether they're employed or not. Then they receive job offers or are fired. And the unemployment rate at date T is U of T. Now let's write down the value functions for these folks. We're going to have two value functions. If you're unemployed, then you're going to get V sub U. So unemployment is your state. If you're employed, then we're going to have V sub E for employed. However, your state of being employed will not be your only state variable in this case, because jobs will be distinguished by their wage. Not all of them will be the same. So this will have to be a function of W. Now let's start out by writing V of E. And here comes another useful convention that occurs in the discussion of search models. It's a convention that's going to be a bit different from what you would normally see in a dynamic programming model. Now, here is how we've been talking about what happens inside a period so far. Say this is the beginning of period T. And here's the sequence of events that occurs within that period. And here is the beginning of T plus 1, and time continues. At the beginning, the agents consume, and then they make their decisions, then they receive information about the future, and we're off into tier plus 1, where maybe there's a new value of productivity or whatever it is that may be random here. In this case, it will be, of course, whether or not they're employed and what their wage is. Normally, we measure value functions starting here. So V of whatever state variable you have is going to be C, or rather utility of C. Remember, in this context, we're assuming linear utility, plus the discounted value of whatever happens tomorrow. But there's a perfectly valid alternative, and that is to measure the value function here. So you've already consumed, you're about to go to bed for the next period, and therefore your value function in this alternative is going to be the discounted value of tomorrow's consumption plus, well, going through the day, V of whatever's going to happen the next period, where you don't need the discount factor here because, of course, as soon as you wake up, as soon as this is measured, it's already got the discounting of tomorrow in it. And in a search context, that's going to be very useful because it turns out that in the discrete time environment that we're using, the value function that we get when we write things down in that way is going to look exactly the same as the value function we get if we were working in continuous time. So now that we've got that out of the way, we want to write down our value function as though we were employed. Our job is characterized by a wage W. We're about to go to bed, so we are discounting everything for tomorrow. Remember, I said that we want to use this representation of the discount factor. So we wake up tomorrow and we get our wage W. Then what happens? Then with probability lambda, we're going to find ourselves unemployed the following period. But with probability 1 minus lambda, we will continue in our job. And that's the value function. What about if we're unemployed? If we're unemployed, we have VU, in which case, again, we're measuring the value function just before you've gone to bed. So the first thing you get is your benefit tomorrow, which is discounted, plus, and here we're going to need some notation. Let P be the probability that you get a job offer. So we're assuming it may or may not be that you get a job offer while you're unemployed. Analogously, with probability P, you get some value, or I guess expected value, of what you would get as you're employed. Remember that the wage that you get is drawn from some distribution, so we don't know what that is yet. Let's just call it X. And with probability 1 minus P, you remain unemployed. So now we need to find out what is the value of X. So let pi of W be the value to you of receiving a job offer of wage W. The expected value of getting a job offer is then the integral over the range of W of pi W integrated over the PDF. So the next question is, what is pi? If the agent takes the job, of course, pi of W is just equal to VE of W. But, and this is the key thing to search models, the agent is not obliged to take the job offer. The agent may prefer to remain unemployed. Then, what does that give us? It gives us that pi W must equal the max of those two possibilities, VE of W and the value of remaining unemployed. And as a result, the value of being unemployed equals this. We insert that where it said X, and we insert this where it says pi. And that's our value function. What's the solution to this problem? Well, we can rearrange this very easily to obtain that V of E is equal to W plus lambda V of U all over lambda plus R. That's straightforward. Just multiply both sides by 1 plus R. Then the 1 here is going to cancel with the 1 here. And rearrange, you get this. This is pretty useful because it tells us, notice that V of E is strictly increasing. Why is that helpful? Well, look at this problem here. This is a strictly increasing function, and this is a constant. We don't know what it is, but it's a constant because it doesn't depend on any state variables. So what that tells us is that this problem is going to be solved by a particular strategy, which will be for the agent to have a reservation wage. In other words, there will be some wage above which the agent accepts job offers and below which they do not. So we're going to call that reservation wage W star. We don't know what value it has, but we know it exists because VU has to be positive. If you're a silly agent who never accepted any job offers, VU would be the value of getting B forever. As long as B is positive, that's a positive number. Of course, that will be better than accepting a job offer of 0. Observe that this expression, the expected value of a job offer conditional on having received one, can be rewritten as follows. I can subtract any constant from this, from both sides, as long as I add it back at the end. And so I've decided I'm going to subtract VU from both sides and add it outside. It's not going to change the behavior of this agent. Of course, this then becomes simply 0. And that means that this equation here can be expressed somewhat differently. Let's multiply both sides by 1 plus R. So that's gone. And now let's rewrite this in this manner. It's all multiplied by P, so you're going to get that, which of course translates into this coming out here and being multiplied by P. After which we can simplify by, well, noticing that these two things together just become VU. And of course, this VU cancels with the 1 times VU over here. And now we're left with something simpler. Next step, we know that below W star, the value of this integral is 0, exactly. And above it, it's going to equal this. And so what we can do is instead just rewrite this in terms of W star. And that's going to be correct as well. What's the financial interpretation of this problem? The financial interpretation of this problem is that, remember, R times the value of some asset, whatever the asset is equal to the expected value of what you get each period. It's the flow value of holding that asset. So the flow value, what you get each period from holding this asset, the asset is the state of being unemployed, is you get this payment B, and with probability P, something might change. With probability 1 minus P, nothing changes, and so there's nothing to keep track of. With probability P, what do you get? You get the expected value of receiving a change in your value function. So very often search theorists, without going through all of these steps, just write down the value function like this. They know that the flow value of the value function of being in this state of unemployment or any other state is the flow of payments you get from being there, the probability that something might change in your status, and the expected value of that change in status. And here a change in status occurs with probability P and conditional on a wage offer being higher than the reservation wage. Essentially, this is an option value. The flow value of this option, the option of being unemployed, which ultimately is the option of accepting or not a job offer if you get one, is the flow payment, plus the value from exercising that option if it's in the money. And of course, the option being in the money means that it's better to exercise the option than to stay where you are. Of course, this isn't the only equation that characterizes this equilibrium. The other equation that characterizes this equilibrium is the definition of the reservation wage. We can set this equals to W star. That has to be true, just by definition of VE. But for the case of W star, these two things are equal. Therefore, this is also equals to VU. Rearranging this, we get simply the equation that W star is equal to R times VU. You can see that simply multiply both sides by lambda plus R, subtract lambda V from both sides, and we're done. That's it. So our equilibrium is characterized by two equations. One is this one, which tells us almost everything we need to know. The other one is this one. Third, we have this, but we can plug that into here and eliminate VE altogether. And we can simplify this. You can multiply top and bottom here by lambda plus R. Now we can put these two fractions together over one denominator. And we realize that lambda times VU is redundant here. And we have this expression, which is much simpler. So now we are down to two equations. This one and this one. And we have two unknowns, W star and VU. Everything else is being eliminated. So how do we solve this? The way these search models are often going to be solved is more or less graphical, or rather you can use some graphical intuition to prove that an equilibrium exists, at least under some circumstances. So what graph do we have in mind? Imagine a graph, we'll draw it in a second, that has W star along the x-axis and VU along the y-axis. This equation is pretty easy to represent in that space. So let's do that now. So now let's draw our two axes. Here's the vertical axis. Here's the horizontal axis. The horizontal axis is W star. The vertical axis is VU. And our first equation, do you remember, was the equation W star equals RVU, which of course is a straight line. What about this function? Well, this function has the following shape. First, let's set W star equals to 0. If W star equals to 0, then we would have just this expression. If you rearrange now, we can take this outside. And notice furthermore that minus RVU is just a constant. So we can take that out of the integral as well. I guess to take it slow, going to end up with the following expression, where this is now just W. This is now just RVU. Of course, we can take RVU outside here. And the value of this is just 1. Now we can add this to both sides. Collect terms. Divide both sides by this, by what's multiplying VU. And we have that VU, if we assume that W star is 0, is positive. This is B. This is the expected value of a wage offer. And this is just some factor, as is this, both of which are positive. So we know that in W star VU space, when W star is 0, this line crosses the VU axis at a positive value. What else can we tell about the shape of this function? To get a sense of that, we'll need to take the total derivative of this function with respect to W star. So let's do that. Total derivative of this with respect to W star is going to equal the following. Well, that turns to 0. Next, we can apply Leibniz rule, which means that we must subtract the value of this expression evaluated at W star and then we need to take the derivative of this with respect to W star. Now notice, this is not W star. This is just a variable of integration. The only thing that depends on W star here is that. And so what we get is this. So let's just put the minus outside. Indeed, we can take this whole fraction outside. Very good. Now let's rearrange, collect terms. And that means adding this expression to both sides. Factor out this derivative. And divide both sides by this expression. And we end up with this. So, first thing to notice is that this is a positive number, whereas this will have a sign that may vary, and it will specifically depend on the sign of this. So just to make that dependence, let's put this outside so you can see better. That should be evaluated at W star. Remember that for the reservation wage, this is always true. So if there is a reservation wage, this is going to equal 0 at that point. In other words, the reservation wage will be a turning point for the function VU of W star. In other words, for this function, if there is one. If we are below the reservation wage, then since we know that this thing is an increasing linear function, if we're below the reservation wage, then this is going to be a negative number, because remember, the line VU started above this line. This line crosses the origin, but this one at the origin, as we showed here, is positive. Therefore, starting out from 0, the derivative of this function here, VU as a function of W star, is positive. If we ever cross the line, however, then this will then be negative because it flattens out. And so that means that we will be able to cross these two lines at most once. Let's go back to the picture to get some geometric intuition. So here's what we've shown. Again, remember the first line W star equals R VU is an increasing linear function here with slope 1 over R. And the other one starts at a positive value here, and therefore, since it's above this line, its derivative is positive. But if it ever crosses the line, it has to do so at an inflection point. It has to do so at a turning point, after which we show its derivative must be negative. Therefore, they can cross at most once. And so what we've shown is that if there's an equilibrium, it must be unique. Now, why is that important? That's important because what is an equilibrium in this environment, or what is a solution rather? It is precisely a W star and a VU that satisfies both of these equations. And therefore, any solution here is going to be a dot where these two lines cross. And we just showed that there can be at most one. The next question is, can we guarantee there will be any such points? For that, let's return to the equations themselves. Next, how do we get existence of the equilibrium? Well, intuitively, we need the following. If, of course, B is greater than W upper bar, then there's never any wage that's going to persuade you to take a job. You'll always prefer unemployment. But if W bar is strictly larger than B, there will always be some wage that you're willing to accept, and so you be able to guarantee existence that way. Now that we're done with the general analysis of this model, let's do something with it. Let's say that into this environment, you introduce a change in the unemployment benefit B. How's that going to change the equilibrium? Well, B doesn't show up here, so this equation doesn't move at all. What I'm going to argue, however, is that B is going to raise this line. It's kind of intuitive, I guess. If you get it paid a larger unemployment benefit, it means that the value of unemployment goes up. It's not lowering the value of being employed in any particular job, and so overall, it should raise this line. And of course, if you raise this line, it means that your reservation wage should rise. So it's telling us that if you have a higher unemployment benefit, people will become more selective in their jobs. Now, one variable that we haven't talked about much yet, that of course is important for labor economists and for macroeconomists, and which does exist in this model, is the unemployment rate. So now let's look at that. So the unemployment rate, which we called U, is not in general something that's going to be constant over time here, so let's write down how it evolves. So the number of unemployed people at a date UT should be equal to the number of unemployed people at the previous date plus anyone who was not unemployed in the past but who was unlucky enough to lose their job, which happens to each one with probability lambda. On the other hand, there may have been some people who were unemployed in the last period who found a job. So we have to subtract by the mass of people who may have experienced a job finding. So with probability P, each person who was unemployed gets a job offer. Of course, it's critical to remember that just because you got a job offer doesn't mean that it was acceptable to you. So you have to multiply by 1 minus the probability that you got an unacceptable offer. And what is the probability of an unacceptable offer? It's the probability of getting a wage offer below the reservation wage. And of course, that is just F, big F, the CDF of W star. Now, we're going to be interested in the steady state, at least for now. And so the steady state unemployment rate is something we can find by just deleting the time subscripts. Now, this of course becomes 0. Subtract U from both sides. Now expand these terms. And we can collect all terms that have U in them over here. Factor out U. And we have found our steady state unemployment rate. And the key thing to observe here is that there's going to be a link between not just the parameters here and the unemployment rates, but also between the reservation wage and the unemployment rate. In particular, the reservation wage goes up. The probability of getting a job offer below the reservation wage rises. So of course that means this declines, the denominator declines, and that means that the unemployment rate rises. The unemployment rate rises with W star. And you may remember that we were discussing before that B raises W star. Therefore, the unemployment rate, the long run unemployment rate, rises with B. Now that's intuitive, of course, and suggests that this is the kind of thing that we can do with search models. We can see how in the long run changes in various parameters can affect unemployment rates. We can do all sorts of other things. We can also use them for business cycle analysis, as well as for policy analysis. However, this particular model isn't going to be that useful for either. And the reason is very simple. This is not a general equilibrium model. There are two things missing that we would want in order to say anything substantive about policy here in particular. One is that we don't know where B comes from. Is it funded by taxes? For example, that's not modeled here. Another is that we don't know where the wages come from. There's no wage setting mechanism. There's just some exogenous distribution of wages. And that would be something we'd need to endogenize to say anything about general equilibrium. Finally, since there are frictions here, there's a probability of finding a job or a probability of losing one. If you think about how the labor market works in reality, you'd think those are things that are also endogenous. People don't lose their jobs for no reason. They lose them because there was some problem at the company or some problem with their boss there, some bad match of some kind or another. You'd want that to be endogenous. And of course, that all suggests that if you generalize this and make it a general equilibrium environment, there will be informational or other frictions that mean that the equilibrium is not necessarily going to be efficient. And so for all those reasons, generalizing this model to a general equilibrium context will be important in order to say anything about policy analysis or the business cycle. Thank you. I hope you learned something, and we'll see you in the next class. Bye.